So, okay, that said, let's get started with today's lecture. And I believe last time Wang Peng actually gave a lecture. I was at ICCB. Also, last week, I also heard you guys, so many of you supposed to attend the AI forum with quite a few very good people. We are lucky to have them, right? Speak about a different work. Incidentally, we'll mention some of the work today, right? You can see some of the professors from some of the top universities, right? They're already working on very different perspectives, right? They come here. We have a session under the Future Prize, Science Prize. The 5 people: Zhu Jun, Tsinghua, Wu Jiajun, Stanford, Qu Qin, University of Michigan, and also the Xie Sanli, NYU. Right? They gave us some lectures, right? So after the lecture, there's an audience actually commented that this is one of the first computer science session or forum they attended in the last 2 years. Actually, no one talked about the language model, right? Right. So you can see the top professors in top university they're already going beyond. Okay, they're looking forward. What's done is done. Right. Unless we can understand what we have done better. That's what this course is about. But then the question is how do you go forward, right? What's missing, what's not done? That's your chance to make a mark. You have to find your own legacy, right? So, and you have a chance to do that. And as we'll point out through this course, right? Not only to understand, not only just understand what they've done better. I think Professor Wang Peng did last week, right? Help you, right? There is a principle way to derive, right, from the principle you learned in this class. To derive the architectures. And not only understand, explain what the deep networks is doing, and some of the popular networks doing, but also allows you to better simplify them. Design new things, right? Go beyond. And today we'll tell you how much less, how much more you can do with it, right? And I'll start to do a little bit of recap, right? What is our objective and how we achieve that objective correctly, right? And right, throughout this talk, and in fact, even at the conference, right, the forum, you can see that this is the people are actually in deep learning or intelligence as very much on the theoretical side, everybody is converging on this mental picture, right? What is learning all about? At least learning data distribution or developing a memory, right? Learn from data is all about. The mental picture kind is that we have very high dimensional data, right? And they lies on very low dimensional structures, distributions. Right? We're trying to find where they are and convert them to some highly compacted structure. Become our memory, right? Do a copy of this. Again, two process, right? First of all, how to find it, where the ROM is. Second, how to transform it to something structured. Okay, how to find it is using denoising, compression. But how to make it structured, transform, right? Linearize, expand, right? So you can see in this case, the original success of classification is actually precisely doing a very, very baby version of this, right? Doing the grossly lossy version of this. Convert entire curve, entire class surface manifold into a single point. Right? And learn a very simple code for the entire class. All images of Apple become 1000. Okay. Very simple code. Find a very simple code book to represent the entire objects, right? For the images. Of course, we're trying to say that that's too simple. That code is too simple, right? We lose all the characteristics of the data. Like how many different types of apple, what the individual apple looks like, right? Next, you want to actually keep that variability in each class. Still also make each class simple, right? Make the class of apple a linear subspace. Right? That's actually key. So we really try to learn linear discriminant representation as our memory. We try to memorize. It's easy to memorize. Also, it's very easy. Why do we memorize things? We want to use it repeatedly and very efficient when we need it. Okay? So if you memorize things like this, it's very hard to find where it is. If every time you want to access your memory, you have to go through a sampling process, very expensive iterative process, and you cannot even guarantee where you end up with, that memory is useless. It's only useful to produce some pretty picture. It's only useful for you to dream. Okay? Close your eyes, dream about it. It will be no useful for you to predict in the real time. Okay? To access the relevant memory in the split of a second and use it for prediction. All right? Understand? So you need a very structured memory, right? High structure. Hence, it's not just a simple compression. Right? Compression is not the only purpose. It's also organization. It's important. So of course, one measure, right, to measure the goodness of the representation get. So the course is what we call the information gain. Right? We try to maximize the whole minus the parts. Right? Somehow this very interesting, similarly simple, but actually magical measure, right? To maximize the representation of the whole data sets versus the parts, intrinsic structure, the difference. And then it will automatically help you to organize things in a very structured way, right? So we call it maximum coding rate reduction. Right? Reducing the coding rate exactly corresponding to the gain in information about where the data is, right? Where the distribution is. It's very easy for you to remember, right? And of course, right? How do we memorize? How do we get our representation better and better, right? We try to learn representation, maximize this object function. Then this looks complicated. At least what minimum we can do is do a gradient descent, right? Take the derivative of this object function and make it better. Go to a higher place, higher ground, right? Climb the hill, very simple. Then once you compute, you notice, like this derivative is exactly equal to this form, right? Each term looks like this. This is exactly the autoregression residual. I give you a residual net. And when you enforce invariance, translation invariance, this operator automatically becomes convolution. Hence, convolution is not what you want. It's a result. Right? It's derived from what you want. OK? 明白吗？不是自其然，而是自其所以然。为什么 ？Because we want to compress all the translated version together as one group. Then this compression operator, this matrix becomes a convolution. Okay, right. Here I only use one more term, 哎，其中一个 term， 对不对？这实际上是一个派，对不对？想派 ，that's pi. No, if I don't like this, because this guy is very hard to compute, right? It's very big matrix, take inverse. Although it has some structure, I can still compute it, right? In the frequency domain, it's easier, but still, it's a lot of work. Okay, if I don't like it, I can expand it, right? Take a Taylor expansion, 1 over 1 plus x, which is approximately equal to 1 minus x, right? Take that term out, multiply the z, you get this expression. So what this expression looks like. Again, don't forget, right? Here, I'm just pulling out the first term, right? I'm using the first term example, but this term looks the same, right? Has the same form, but except there's a pi in between, right? There's always a pi in front of z. What the pi is doing? Only associate which data, which part of z belongs to that part. Remember, last time that's exactly what the query is doing, right? Sort out which data is actually belongs to which subspace. Okay. And in general, you don't know that membership. It becomes the parameter you want to ask. Okay. Which subset of z belongs to the group J, belongs to that subset. Okay. And you want to learn that type. Hence, you can visualize there is always a plot, right? Matrix V, W, K, whatever you call it, some linear matrix, sort out which Z belongs to each head. Right? If you do that, you get exactly the attention pattern. Right? So basically, after all these years, right, trying and error, you actually end up with finding something extremely simple. You're just grouping things and try to estimate which tokens belong to the same group and to do a denoising. Okay? Which sense, right? Using data, first find out which data belongs to the same group, and use the data as a regressor to each other, so you guys all line up. Okay? Any error, correct yourself. If I see any error, I correct yourself. That's it. That's what those each operator, this operators would. Hence, each layer is exactly has this form. Then you can call whatever this is. You call this, if it's a shift transfer, then this operator will be convolution. Call it a CNN. Or there's a skip collection, call it a residual network. Or there's multiple channels, call them experts, mixture of experts. Okay? And because the form, call them transformers. Because they're all approximating this thing. If you want to break down what the C channel looks like, break this C and E using this. Instead of that, you get transformer like operators. All right? Very simple. So everything just comes from here. All right? They're all actually approximating this thing. That's it. Right? And it's simple. And everything is fully explainable where it come from, where all this architecture come from. Or all this variance architecture, all essentially trying to approximate this operator. And this operator, conceptually, we talked in chapter 3, right? But it's exactly what very similar to conceptually is also doing exactly like the score function. Okay? Reduce noise. This is exactly reduce the noise. Okay? This is exactly a lossy version of the score function. This is the noise. Right? What is viewed as noise? The residual of autoregression. We're reducing this term. Okay? So the self-regress. Right? Anything I do not agree with the group I belong to, I correct the data. That's considered as noise. You remove it. Right? You push everything into a lines and the higher probability switches. So this actually, I really believe that now you can see that this goal of finding where the distributions, the concentration, also transform that support into linear is exactly explained what the modern deep networks do, right? Layer by layer. And the goal is try to maximize information gain, right? Measured by the information gain of the final representation you got. And also, of course, it's also interpreted as coding rate reduction, right? Reduce coding rate. And the layers are just iterative optimization. And each layer is actually doing gradient descent. Although the gradient descent can be written down in different forms. Right? Is it no mixture? It's called. See, just like there are so many gradient descent algorithms in the world, right? Hundreds of them. Everyone will approximate gradients in different ways. It's fine. Yeah. 这个你爬山, you climb the hill. From the bottom to the hill. Not every time it goes through the same path. Okay? Right. Well, if the goal is to reach a peak, right? 你先缓一点，再急一点，陡一点，或者先陡一点，再缓一点。Why it's up to you? Right? 条条大路通罗马. Right? All roads to Rome. Just a matter, I control it. Hence, all the variants of neural networks are actually doing just a different way of reading set, right? And of course, you can say then if you strictly enforce variance. And that algorithm is, like you can see, right, in the redo, in the create. In fact, if you have the redo, you can actually initialize the forward fashion. And you can also learn. If you are not happy, the iteration is not, the operator is not effective enough, it's not efficient enough, optimizable. If you can afford it, okay, can afford it. If you repeat the 30 steps, if the results is not good enough, you know the ground truth, use that error to backprogram, make sure each layer is more effective, gets closer to what you wanted. That's called supervised learning. Okay, supervision, supervised fine tuning. Okay, so you can make the layers more efficient, at least for the data sets you have. That's exactly training the neural network using backpropagation. Right? Understand? And the whole network, you know what each layer is trying. What the statistical, geometric operation that each layer trying to operate on the data, getting into that particular layer. Okay? And we can also measure whether or not that output of that layer really gets better or worse in terms of the measure you want to optimize. Sparsity, information gain, rate reduction. Okay? Right. And of course, if you train everything well, you have enough layer, take enough steps, if they train well, the final representation, the output, final output of the network will be exactly what you wanted. Right? Exactly what you wanted. If you have enough data, have enough layer, train them well, converge, their representation are indeed a mixture of orthogonal subspaces. Right? Rather than right, something still entangled. Although you can still get a very high score in terms of classification, but this really is not going to help you to do other jobs. Okay? We'll talk about. Now, this is about the one-way optimization, right? We still have this is still a one-way ticket, guys. Today. We all from the experience of 爬山，对吧？有时候会迷路，对不对？You might get lost, you get stuck, right? Or there's two hills, you reach the peak of the solar farm, right? There's no way to descend anymore. It's not immediately, right? So you can get stuck with. How do you know? I mean, if you just do optimization, if each layer is trying to optimize in a greedy fashion, but there's no guarantee the solution, the end, is correct. Right? It's complete. Right? How can I guarantee this one is good? Right? Because this way is doing the greedy optimization. Right? Could get stuck with local minimum. Right? Maybe there's 10 classes, you only end up with 8 classes. Right? Some classes you still are able to separate. Or the apple, this red curve, maybe in 5 dimensions. There are 5 types of apples. But for some reason, the subspace end up with only 4 dimensions. Or there's some noise in the apple image. You end up with this subspace is a 6 dimension, which means there's one more dimension still noise. We're generating something that's not quite apple. Okay? Right? How do you make sure this thing, this structure, and this one is an image of that? Is a world model. Is a model for the world. Okay? How do you guarantee this? There's a sort of code up for the one-one mapping. Of course, from mathematics, it's easy, right? If this is an authentic copy, transformation of this guy, I didn't lose anything, then I should be able to go back. Right? Should be able to go back. So actually, it turns out that's probably the only way you can check if your memory is right. It's complete, right? And later we're going to talk about there's actually another reason you have to check. Right? Because what if in the beginning the data is the points are not even enough to identify this distribution itself? Okay. There may be still one type of apple I've never seen in my life. right? Hence, even me at that age 50, I still cannot claim my memory of Apple is complete. Remember? Because the data, this distribution itself is not complete. If I see a new sample close to Apple but still different, I may still have to memorize it. Hence, I have to update. I will talk about this later, right? But for now, let's assume my data cover the entire distribution. But even though I still have to worry, the optimization may not be perfect. I may get stuck with some solution, partial solution, right? We'll talk about how to modify later. But from that previous example, you already know building memory is not a static task. Okay, it's not a task of get a hold of the entire all the data sets and learn a model. Then you're done. No, it's not. Right? Our memory has a mechanism. By definition of memory, it's a dynamic notion. It constantly gets updated. Right? There should be the mechanism to constantly optimize or update our memory. All right, we'll talk about that later. So first, how do I check my memory is right? I need to be able to go back. We call this decoding. Decode my memory, right? Here I see images comes in. I realize this is apple, orange, right? Pears. Now, if I think about here, close my eye, imagine an apple, I'll be able to decode it. Right? Hence, encoding, decoding. I constantly see something, I can see something new, something in front of me, I can recognize it's something I've seen before or not, right? Be able to decode it. Hence, we encode, we try to make, suppose our data lies on multiple manifolds, right? Each class is another manifold, some no dimensional, it's a 5-dimensional surface. We make it a 5-dimensional linear subspace, right? And maybe make them discriminated. And also, I should be able to take these, go back to that manifold. Take Sj, go back to manifold, right? This is decoding. I want this mapping to sort of almost one mapping. Okay. Right. So hence we want to achieve an so-called auto-encoding. This is called auto-encoding. Right? It's kind of close the loop, right? From X to Z back to X. In this achieve encoding F, decoding G. Okay. Clear? This is the question. Right. If for some reason I can find that the F and G are mutually inverse of each other, right? I can get an authentic copy of X. X hat is the same as X. If I can check that, then this memory is complete. Right? Now you see, okay, you see why we go through this stupid trouble. Right? If I want an auto-encoding, there's a trivial solution, right? If I want X hat to be the same as X, there's a trivial solution. What is it? Right, there's a very trivial solution. If your goal is just to get the X hat equal to X, right? You learn identity map. Why not? Why in the world do I want to do Z, right? I just in the origin space just memorize it. Of course, this is expensive, right? So the whole purpose, again, of this transformation is to make sure Z is simple, structured, right? You know that you get explicit dimension reduction, because this one is curved, right? In the origin space, a curve, if you take convex top, can maybe span very large space. But once you identify the intrinsic structure, make it linear, this dimension becomes very low. Right? This is compression. Second, it's a structure compare. As I said, right? This is extremely hard to access. Yes, you can learn diffusion map, access it. We talk about that in chapter 3, right? But you have to sample its experience. Also, the control is very hard. You don't know where it's from. Okay, it's very hard. Of course, people do all kinds of Wang Yang, sure, right? try to do control net, to do all the stupid fine tuning, right? Well, but our brain doesn't do that. Our brain actually organizes it, and we access this part, then we decode whatever we want. How do we do this? Right, this is important. Get it? So that's why I make the solution non-trivial. Otherwise, if your job is just to learn some x heading to x, just to learn z have a lot of requirement. We have a lot of hopes for it. Okay, has to be linear, has to be no dimensional linear subspace, and also has to be almost incoherent, discriminated. Clear? Then the problem become meaningful, actually become extremely hard. Okay? Right? Actually, Hinton spent about 20 years on this problem. Right? In fact, his Nobel Prize winning award is actually related to trying to solve this problem. Although unsuccessfully, he still get the recognition. So now let's try to make this a little bit formal, right? Right. We want to learn a good reputation from our data, right? Our data like this, we try to make sure FMG are some kind of smooth map, continuous smooth map. It's not something crazy. And also, they're actually also encoding, right? And so if you want to make all the classes orthogonal to each other, it's kind of that the ambient space has to be larger than the sum of all the intrinsic dimensions. Okay, this is just a technical condition, right? In reality, is that as long as the ambient dimension, the feature space, the dimension is long enough, you should be able to distinguish embedded many classes. Okay, a few hundred or thousand. Right? In fact, from this example, right, from this requirement, if you want your features to be discriminated, also incoherent, you want to give the ambient space, feature space, a little bit room, enough room. Okay. So hence the idea of doing the stupid VAE, right? Reduce to lower, doing the UNet is actually bad idea. Okay. Now you understand. Now you know. Although it's very, very popular. Okay, people wrote about 10,000 papers about it. Actually, conceptually, it's something you want to do. Right? Surprise, right? People will keep working on something not quite right for many, many years, publishing many, many papers, and celebrate each other for a long, long time. Right? That's how ridiculous the field is. Okay, guys, you are entering a community that's supposed to be very scientific, but you'll find a lot of ridiculous things. Okay, if you are smart enough, if you are critically enough, right? So we'll get back to what's the right way of doing it. But so actually, you wanted to do the embedding. Clear? So this, what do people call, right? The overfitting art. Z is called hidden. Right? Linear. We want Z to be structured. That's a hard part. Right? Linear. Now, of course, this is not a new problem, guys. I mean, there's people think, and also including everybody. It turns out that people have been working on this kind of problem for like hundreds of years. Okay. PCA is the first example. Although the start with the data is not as complicated, right? Here is multiple curves, right? Surfaces, right? Multiple classes, nonlinear surfaces. But if you assume the data distribution is very simple, it's already just in the origin space, just a single subspace. We want to find it. Well, that's PCA, right? We find a projection, goes to the subspace. If we want, subspace can get it re-embedded back using the inverse map, right? V transpose, that's projection. D, right? Of course, then we can make it slightly harder. Instead of one subspace, maybe K subspace, 2, 3, 4, right? Mixture of subspaces. And we might make them orthogonal and do that. This is actually what we call the either sparse fiction learning is one example, or generalized PCA is another example, right? People work on this kind of assumption. If you assume the data, the original data X, the distribution is already reasonably analytical, right? Already a mixture of subspaces. Then there's already existing solutions. People have tackled them for many years. Okay. Well, about the 1980s, Creamer talked about what if my data is not linear? I mean, those are still linear, right? And it's locally linear, mixture of Gaussian, mixture linear. But what if my data is actually some kind of a manifold, right? It's a submanifold, some non-linear, right? Then of course I want to make sure it's if it's a non-linear manifold, I want to make it linear, right? So reduce to some little d is lower than some manifold. I want to linearize it, then getting back. So this is a little bit harder problem, right? I have a curve. I want to make it linear and also learn mapping from that curve to a straight line and also remember that mapping to be able to go back, right? This is called a nonlinear PCA. Actually, but Hinton renamed it, called autoencoding. Okay, it's Hinton's name. So, but you can see the very natural extension from the problem people have been worked on for hundreds of years. Of course, the real problem that today we are dealing with, right, through generative model, right, we're dealing with many categories of objects, right, images. Then we're dealing with many classes. Each class may be in the manifold, class of images in the manifold. And we convert them to some simple. Simultaneously, we want to convert all the classes into highly structured subspaces and distributed into our brain, right? Then we'll be able to regenerate whenever it's needed. Okay, that's the problem. Clear? Now let's go through. But this is what we want, right? But before, how to do this may be a little bit complicated. But let's learn a couple lessons, right? Learn what we have been doing in the past for those simpler cases. Try to borrow ideas, guys. See, don't get very easily convinced whatever people are attacking the current problem, right, is the right way. Right? Turns out if you can know a little bit of history, all the similar problems, even simple version, how people attack them, just from the solution, how people approach this problem, you can get likely much better ideas to solving than any of the paper. Right? They try to attack problem like this in a heuristic or some of the empirical way. Okay? So that's a lesson I have learned my life. A very valuable lesson. Okay? 你经常我说嘛，太阳底下没什么新鲜事儿。Turns out, actually, people forget many things rather than they actually create new things. Okay? The chance the entire community or many famous people actually forgot or didn't know what have known before. There's much higher chance than they actually create something new. Okay, remember, we're living in this world. I want to repeat this again, right? The chance Ima, I do not know what I have done in other fields or related problem. Or the chance I have forgotten what I have done in the field is much higher than I have the chance to create something no one had known. Okay? Think about that. What is all? Which probability is higher? That applies to every single scientist. That applies to every single paper. That applies to every team of researchers. Okay? Sometimes even apply to the entire community. So you know the relationship, how the idea is a progression. This is what we call scholarship. We keep the scholarship as community. So we know where we come from, where the problem are related, where the ideas come from, right? And give the credit. For example, PCA. PCA is very simple. We try to, because we already know the data lies on the low dimensional space. So we can directly project that in the high dimensional space to some lower dimensional space, right? We just have to find what is the proper dimension and find where that basis is. Right? We can directly, the final representation we know is already on the low dimensional subspace. Remember, because the diagonal is already compressive. Right? We can directly go to a lower dimensional space, lower than the previous ambient space. Right? Make sure we find it. And make sure we find the transformation U, and also lift it back into right. So this is what PCA is doing. right? Again, there's a algebraic solution, there's a geometric solution, there's a statistical solution, right? A huge, very rich history, right? Well, turns out, right? Despite all this beautiful algebraic solution, geometric solution, right, statistical solution, we never used any of them. Right? The actual solution we use, algorithm we use, power solution. We do a power solution. Right? I told you, right? This is the denoising algorithm. Okay? Just because you didn't recognize it yourself doesn't deny this is exactly what the denoising algorithm is doing. Okay, this is denoising. We first diffuse to a random vector. This always bring you back to the first principal component. Right, converge to one-dimensional space you want. Okay. And it turns out this is the most efficient algorithm to compute a singular value, right? Compute the singular value binding the principal components, one after another, right? The whole world is doing this. Except our brain is not doing this. Why? We don't have that option. To compute our algorithm, we need to get all the data, all the samples, thousands of samples. Each column is one sample. Okay? Apple 1, Apple 2, Apple 3, Apple 1,000, 5,000. Okay? We get a convert. We get a whole matrix. Okay? We get a whole batch of data. We never learn 一次吃500个苹果吗？而且还是不同种类的。Right? You learn apple in that way. Pears, chicken. You never do that. Later, we don't have this star option. We cannot collect all the data with, well, I think this is enough. No, let's start early. Okay? 从小到大，先收集10年的苹果再收集10年的这个桃子对吧？见过的东西先收集起来，照个照片保存在那儿。等到够了以后，哎 ，let's try to compute the principal components. Let's try to memorize what the apple looks like. You don't do that, right? We never had this stupid option. Okay, forget about it. We don't do that. We cannot afford to do that. Then what do? We do one sample at a time. Turns out, yes, you can. If your data is indeed lies on a single subspace, you can design very simple. Again, start with a stupid random vector. Okay? Your brain has nothing. There's nothing about. Then hit X, then updating this very similar power iteration rule. Right? Hit this with this content. It's a little bit of hit with something, a little bit of correlation, and plus some update rule, and normalize it. Some nonlinear operation. Linear, nonlinear operation, right? Actually, if you look at this, this looks very close to the token statistics. Okay, this is a quadratic index. You hit it once with some vector, you hit it again. Compute the correlation and use it as a ways to update. Okay, if you look at it, this is already very similar to what token statistics is doing. Okay, it's very cheap to do this. And then it's the same. And also the way is this is online algorithm. You do one sample at a time. Okay, you update U based on one sample at a time. Every time there's new sample, you update U a little bit, update a little bit. So in the beginning, see, maybe one cortical column in your cortex, right? It's allocated to remember what apple is. In the beginning, it can be something stupid random. I have no idea what apple is. But whenever I have an apple to set, I start with random weights. I had updated this area a little bit. Well, this is something I've seen before. You should try to remember it. Build an image for it. Build a code for it. Right? Compute what's similar. Right? This you get better and better. Eventually become the first principal component of Apple. Then you start with the second one. If your coding column has another dimension, third, fourth. Okay, you can do that. And I can assure you guys, okay, this is the only online algorithm we know for linear subspace. For any other distribution, nobody has any clue, no algorithm like this. First of all, this suggests doing online computing a structure representation is possible if the distribution is simple, almost linear. This suggests it's likely our brain is doing this, okay, because our brain is doing online learning. One second. However, how this is applying to even the mixture subspace, let alone mixture, a nonlinear surface, nonlinear manifold, or a mixture of nonlinear, nobody has any clue, okay? All we are doing today is what? Batch, right? The bigger the batch, the better, right? And also global optimization, all this parameters together, right? So this is the only algorithm we know in 1982, since 1982. Nobody knows any other. Well, of course, there's a lot of stupid heuristic algorithm, okay, but this is a provably correct one, okay? For PCA, yes, you can do this, okay? Of course, there's a tons of heuristic online learning, one sample at a time. You can propose many, okay? But this is the one distribution we know. There's a guaranteed algorithm procedure to get hold of correctly. At least I don't know. If you guys know any other big shell subspace, let me know. Right? Nonlinear PCA, let me know. Right now, we're doing an option. We're doing all our algorithm, including the power iteration. The solution we are computing is a solution that nature does not even have an option to afford. Okay? That's how far we are from what nature is doing, guys. How nature forming the memory is far, far from. Right? Even Hinton did some neural networks things, but still doing the way that nature, right? Far from what the nature truly do. Okay. Hopefully that gives you an idea, right? How many problems we have about even learning and distribution in a setting that is natural. 好吧，所以现在我们学习数据分布是非常 in a very unnatural setting, right? We call it an artificial setting, right? We collect the billions of tokens, right? Billions of examples, optimize all the parameters together, right? And the nature does not have that option, 对吧？自然界连那个机会都没有，no have that option. Okay, now that's simple subspace, right? Multiple subspace. Well, multiple subspace, remember, right? The notion of compression is a little bit different. Right? Remember, we always pursue what we really compression is defining the intrinsic damage. We don't care about ambient. Okay. In fact, from dictionary learning, right? We talk about this. The input space can be even low, can be very low, right? For example, in 3D space, I can have 1,000 of lines, straight lines. 这个海胆一样啊 think about the 海胆 right? But I can, if I want to make all those lines orthogonal, 3 dimension is never going to be enough, right? 是不是 What I do? Lift them up. I can lift them up in the hundreds of thousand dimensions. Then suddenly all the subspace can become independent, becoming orthogonal to each other, right? So this is the notion of sparsification, right? We talked about this before, right? Or hence, this dimension can be larger, equal, or larger than the ambient space. I don't have to compress because this picture is useful only if the distribution is very low dimension. only have a single mode. Okay. But as long as it has multiple modes, multiple classes, you don't want to do that. You want to keep the freedom so that different classes have a chance to become expand, contrast with each other. 知道吗？你不希望那些数据都挤在一起 ，have no space to expand, right? Too crowded. It's not good to find the simple structure to make the representation simple. 明白吗？ But this is still compression. This is still 400, but it's intrinsic, right? So see, the little d can be even larger than d. This is d. This is the feature space. Can be even larger and equal to d. But the sparsity, the z, the only activated, this vector only have non-zero entries in k coordinates. 明白吗? The k is much, much, much smaller than this one. So hence, this could be 100, this could be 1,000, but this could be only less than 5. Right? That's the compression you are talking about. Okay, we still call this the compressive autoencoding because it's the intrinsic structure we care about, not the intrinsic one. Right? So this is something many people didn't understand, right? This is a very simple concept, but then many people in machine learning actually don't get it, right? They think compression has to reduce the dimension of the feature space, which is actually completely wrong, right? So if I know a data is a straight line, I can embed this to 10 million dimensions. It's still a straight line, okay? That does not expand anything. 明白吗? It's an intrinsic representation dimension you care about. Right? We call this sparse autoencoding. In fact, sparse autoencoding is actually, also people think this is more interpretable, Anthropic. The Anthropic is trying to use this to explain, say that, they're trying to study all the big large language model. They find that in the large language model, the latent repetition is actually rather sparse. Okay? So even the large model, even they trained very empirically, turns out to be able to find all the sparse structures, right? They try to extract all the sparse components and try to explain it, right? See whether or not the large language model has captured some meaningful concepts. Okay, Anthropic spends a lot of effort trying to analyze the sparsity of the sparsity in the large language. Now, all right. We have seen some sparse autoencoding examples, right? At least for simpler distributions, if not the right, for sparse distribution learning or GPCA, right? We're dealing with, for example, sparse distribution learning. Right? We try to learn dictionary. S is data, we try to convert to Z. We think the data is generated by some dictionary, right? X is generated by some dictionary. Linear Z is very sparse, right? K is very sparse, lower than little d, right? Now, if D and capital D, small d and capital D are the same, basically the square matrix. D is a square matrix. We know how to do this, right? That's lecture 3. We're to learn, right? We know how to learn this. And the encoder-decoder is we can convert this to an orthogonal matrix, right? And then the encoder-decoder is very simple, one layer, right? Just like PCA. This is very similar to PCA. But you have to spend some time to find the D, okay? Finding D, you have to solve optimization problem. L1, L4, go for it, okay? Based on prices. But you have to do this in a batch. You have to have enough samples, okay? And it's quadratic in the dimension, remember? If you still remember, right? There's an algorithm, but it's similar to the PCA, very similar to PCA, right? Power iteration. You have enough data in the batch form, do the L4, do the L1, and very similar to ICA, PCA, you get the D, solve. But if this is overcomplete, if this is the fact matrix, if I'm lifting, which means that the dimension of Z is higher than the dimension little d, right? Capital D is larger than, sorry, the other way around, I'm sorry. Little d is higher than the capital D. It's exactly this picture. Okay, how do I get it? Shoot, what's going on? Right? Little d is higher than this, which means the dictionary D is a fact matrix. then this is a little bit harder, right? Then we know from Z to X is easy because once you find D, it's a linear map, it's a one layer. But from X to DZ is not easy, right? It's no longer simple. It has to be broken down to a sequence of mapping. What is called the ISTA, right? You use the solve the algorithm. You use the algorithm to solve Z from X. Use that sequence to give you the inverse map from X, go back to Z. You have to solve optimization problem. Right. Then if you cannot afford too many steps, what do? You make you stop at 20, make those 20 steps as efficient as possible through fine-tuning, end-to-end fine-tuning. That's the deep networks. That's the least. Okay. Lecture 4, we talk about it. You use the optimization algorithm to build the mapping from X to the inverse map. Clear? Very simple, right? Conceptually, it's very simple. I mean, this concept, hopefully, there's a lot of guys. This course is technically is extremely dense and have fast pace, but at the end of the day, I wanted to make sure the conceptual picture should get simpler and simpler for all. Okay? The rest just stay down to spell out what are the technical components. Okay? What we're trying to clarify is what we're doing because the mental picture is actually extremely simple. Right? That's what I want to get. Right? Of course, once you realize I want the mapping from X to Z, just there's an algorithm to do it. That's just it's step 1 to greedy descent, right? Build the algorithm to reproduce this mapping from X to Z. Right? There's some parameters, there's some operator each layer. Optimized if I have 10 hundreds of 100 GPUs. Okay, do a global optimization. Although nature cannot do it, I can do it, right? I have 10 megawatts to burn, right? I can do it, right? So you can do this. So this picture is very, very simple, right? So kind of separate, this is the thing, as I told you guys, right? The concept is important, the problem is important, the objective is important. The actual solution very often not that unique. Okay, just like 爬山，我知道我去爬泰山，自己走哪条路？Right? Find where the sign is. Set that goal is important, right? The rest solution, your solution, I could find a path better than yours. Okay. Well, keep going, right? Find a different algorithm, different architecture, different optimization, right? It's up to you. Now, this is the GPCA. What about the nonlinear, right? So far, those are the two examples, CA and sparse dictionary, assuming still the data is part is linear, right? And it's locally piecewise linear. What if the data is nonlinear, right? The X is some manifolds. That's a little bit challenging, right? So how do we deal with nonlinearity? Then imagine you have to transform something nonlinear to something linear, right? Project on. But here is only one manifold, right? You only have d dimension. The intrinsic dimension is little d, right? This is a very high dimension, capital D dimension. But now we know if I find f, I can directly z if it's a proper dimension. The little d is the intrinsic dimension of that manifold. This should be sufficient, right? There exists such a one-one mapping, right? Z can be an authentic copy of that manifold. Okay? Remember? This manifold only have little d dimension. Right? So such an f, and as long as the manifold is going to be null, and such an f exists. Job is just find it. Right? So it turns out, hence my job is to find such a linear map to project onto the subspace, linear subspace of dimension of little d, and then get back, right? To learn. So make sure that also the points are close to each other, encoding, decoding, right? From the same space, project to Z, I'd be able to go back to a similar plot point, right? Make the auto-encoding. This is what actually people already trying to do. This is what the auto-encoding Hinton set it up, and Kramer set it up, then Hinton worked on this for quite a while, right? But he actually proposed the backpropagation, right? He's struggled with this problem for a long time. Using physical statistics. Hinton 反正是玩这个问题玩了很久啊，he played a lot about the problem. 最早做什么 helpless machine then he find it's very hard to compute, right? Inspired by Hopfield network, okay? Energy minimization from statistical physics inspired. He always borrows some ideas, try to do this. All right, optimize the neural network. He's using neural network to approximate this mapping, right? Then find is very difficult. He proposed the helpless machine. The helpless is very hard to compute, and he simplified it to Boltzmann machine, right? 但是也不好 compute. Then he actually worked on a little bit on minimal description lengths, very similar to minimal coding lengths. All right. Again, it's still very heuristic. And in the end, he kind of gave up. But in 2000, then he proposed, okay, why don't we just do the computational way? He did this kind of just do backpropagation end to end, right? Did a little bit the BP, right? Rediscover BP and try to solve similar problems, right? Now, forget about all these trials, right? Pure trials, but at least understand this problem. Is this problem possible? Yes, it's possible. At least conceptually. People know a long time, right? In fact, it was proven in 1989. If you have a two-layer neural network, just two-layer, as long as it has enough hidden nodes, the W can be very tall and goes through a sigmoid, right? Threshold, like sigmoid, right? Everybody know what sigmoid looks like, right? And then hit it with another linear map. You actually can approximate. You can approximate almost arbitrary smooth function. It's very powerful. That's why neural network can approximate a very general mappings. Okay. In fact, these facts actually have driven people in the wrong way. I mean, at least in the last 10 years. They think neural network can do everything. They also designed to do everything. No, it's not, right? From now with RNS, we know. All right. The nature is not preparing themselves to approximate arbitrary functions. They only prepare themselves to solve very simple problems. The easily solvable problems. Right? They're using the architecture that's specifically for very simple problems. They're not trying to approximate arbitrary. But at least the mathematician likes this, right? So Sebenko actually proved, in fact, Andrew Moore, right, also proved the very general results. Andrew Moore, there's a bunch of people in late 1981. Andrew Moore is in the US. As you can see, there's competition between the US and Russians, right? Somehow, in all this science, mathematics, American prove something, you can always find that Russian has done it before, right? A few years earlier and so on. Right? Which is actually the case here. The Russian actually proved that using superposition of sigmoid function can approximate any of functions. Right? But this is conceptually powerful, but realistically, computation is disaster. Why? This is extremely inefficient. It needs a lot of sigmoid function. Okay? This hidden layer is huge. Okay? Hence, deeper it gets better. Okay? So, although conceptually this is very appealing, but turns out this actually inspired people like Kramer to try to do this with the two-layer network to solve our PCA. At that time, they got very excited. Oh, now we can solve nonlinear PCA problem. We can handle nonlinear mapping now by just using such a simple network. Turns out that they try to tune this, it's never worked. Okay. First of all, even this is not that easy to find W1, W2. They don't have computers, right? Second, they need a lot of theoretically, you need a lot of the dimension. This is huge at the time. There's no way you can afford it. Okay. Then you use a small number of sigmoid, the approximation is never good. Okay. The method never worked. Although it's a good idea at the time, conceptually, but computationally, doesn't really work that well. That's why humans spend 20 years on this, right? trying different ways to simplify it, make it deeper, with a different energy function to optimize those in a very heuristic type, even nonlinear activation function, inspired by statistics, inspired by neuroscience, inspired by control backpropagation. He's basically worked tweaking on this forever, okay, for like 20 years. But his persistence, perseverance actually pays off, all right? So now you understand the history, okay? He didn't start the game, but he played the game longest, longer than almost all people, okay? 所以有时候啊，我觉得啊，又回到那个事情啊，坚持做一个正确的但不 popular 的事情啊，是很难。But very often, right, working on something right, correct, but also not popular, it's the hard, very, very hard way. Okay, because everybody else tells you, right, they're smarter than you, or they are working on something more popular, right? Who are you, right? Everybody else is wrong. Well, very often, actually, that's the case. Surprisingly, see now, but our question now, back to our question, we're dealing with much more general things, right? Multiple. So historically, we're dealing with linear, mix of linear, single linear. Okay. Although the solution not quite there, but now today we're actually facing this problem. Multiple class. Each class might be nonlinear, right? We want to linearize all of them, and we want to decode. We want to recognize. We want to predict. We want to perceive. We want to memorize everything, right? Now obviously there are two things. For auto-encoding, we want our mapping, right? This is close to x. X hat is very close to x, right? That means we'll be able to predict the view, right? Our world model, what we simulate in our brain, be able to simulate the real world very accurately, right? So we can predict. That's the first. Second, we want our memory to be good, right? Z to be good. So there should be a good regularized. Otherwise, right? See, Z has to have good structure, right? By this alone, right? Large model, deep network can never be optimizing what? Kolmogorov complexity, right? Kolmogorov complexity, if you reach Kolmogorov complexity, if you optimize it, the Z will be structureless by definition. So whoever says large language is compressive, is optimizing Kolmogorov complexity, is grossly wrong. Okay? It's misleading. Right? 待会儿我还会 talk about this. Okay? 所以啊，有些人是鲁班 but they will never become Newton. OK， 还没入门呢，连物理入门都没有。OK， 但是这些人是非常了不起的 craftsman， 非常好的 engineer， 但他对于这些概念、理论的理解、概念的理解，可能真的是没有怎么入门的啊。这个世界就是这么简单，有时候啊，不要去神化一些人啊。会做某些事情的人，往往在其他地方会说出一些完全无知的、幼稚的话出来啊。这个人的名字叫伊利亚 ，OK。当然 ，Hinton is saying some crazy things too. Says right. 所以每个人，包括马老师 ，everybody, right? If we stand a little bit beyond our bounds, like a very simple example, right? If we stand a little bit beyond 我们的范围 ，we're equally bad. Okay, I'm no smarter than anyone. Even in the field, I'm an expert now. If I have 10 ideas, I'll be lucky to have 1 or 2 be correct. I'll be blessed. Okay? If wow. We may understand what in the knowledge in the past better than that also. But in terms of anything we don't know, even in the field, I'm an expert. Trust me, if I give my student 10 ideas, I will feel very, very lucky if 1 or 2 of them works out to be truly ingeniously new. Okay? Correct. Turns out to be correct. Okay? That's the fact. 明白吗？对吧？还别说是自己不努力啊，那就不要张着嘴巴乱讲啊。对，已经发生过的 ，if you have a very good scholarship about the historical facts, maybe I know more than you guys. Right? That's the only thing I can safely say about the history, about the few fields I have done very careful study. I may know way more than my student. But anything, even within the field, what's going to happen next? I may have a slightly better chance than you guys. Maybe your chance is 1 out of 100, I'm 1 out of 10. Okay, that's about it. Right? Even the top, nobody's God, okay? Even in his own field, right? So be a little bit humble, be a little bit scientific, right? So that's why I want everybody to be critical about what you are doing, what your pals, teammates is thinking, and even what your professors think, right? Even the whole community is thinking. Be critical, be self-critical, right? So this is actually the first step to have a chance to be critical. So how do we do this? Right. So we want Z to be structured, right? So then we want to pursue really what the heck is the right distance, right, for data, for rate management, right? Sometimes the distance is not that easy, right? Same for images or 3D world. Again, sometimes not only certain data, it's very hard to compare the distance, especially distribution distance. Again, in nature, sometimes I told you guys before, right? Nature sometimes don't even have the option. We don't measure my estimation of that distance. We don't measure every single time I see something. Okay, I don't have a ruler. Right? You don't can compare this. No question of how we learn. Hey, so can you take a break? Yes, yeah. We can take a 5 minutes break, all right? This is a good time to take a break. If you have any question, you can ask me.